Hello, my name is Ian Oakley, and I'm a professor in the computer vision at KAI's School of Electrical Engineering. Today, I'm going to talk to you about mobility and wearable devices and some of the work we're doing in this area. Before I begin, I'm going to introduce briefly my lab and our main area of research. Specifically, my lab is the Wearable and Interactive Technology Lab, and we work in the area of HCI, or human-computer interaction. HCI is defined as a discipline concerned with the design, evaluation, and implementation of interactive computing systems for human use, and with the study of the major phenomena surrounding them. So what you can take from this is we're ultimately concerned with not just developing technologies, but understanding how people use technologies and developing technologies that meet people's genuine user needs. We're concerned not just with technologies, but with people and the intersection of those things. The other thing I like about this definition is that it states that HCI is inherently interdisciplinary. So a successful HCI project typically incorporates perspectives from multiple disciplines. Specifically, technical component is a core element of most HCI projects. We need to build systems, we need to write code, we need to develop sensors, we need new ways of working with digital devices, and that entails substantial technical development. But this is not enough for a strong HCI project. We also need to focus on people. And to do so, we often leverage methods and approaches from the discipline of design, and particularly focusing on user needs and keeping users at the center of our work and our objectives. This is not enough also for a strong HCI project, is after we have developed systems, after we have focused those systems on user needs, we also still need to determine if they meet our original objectives. And because they involve people, typically we need to recourse to methods from behavioral and social sciences to do so. So in these cases, we conduct rigorous empirical studies of how people perform with their systems in order to characterize how they perform. So the projects I will talk about today, the work I'll talk about today, you will see elements of all these aspects in those projects. So what specifically do we do in this big area of HCI? Specifically, my lab focuses on the design, implementation, and evaluation of novel input and interaction techniques. I call this generally nuts and bolts HCI. So what we're generally interested in is we're interested in how you actually control devices, how you select objects, how you read, how you type, how you swipe, how you control the kind of digital devices that you have. And particularly the kind of devices that we tend to be interested in are things like mobile devices, like your smartphones, and increasingly wearable devices like smartwatches and smart glasses. The kind of input technologies we focus on specifically have historically, and in the work we'll talk about today, also focus on things like touch. We have a long history of working with touch input. Also the opposite side of touch input, which is haptics. In these cases, we're dealing with devices that push back or vibrate back to communicate to their users. And finally, also sort of richer aspects of touch input, such as gestures. So here, rather than making an explicit input like a selection, users are making a shape or some other form, and we're using that, interpreting that in order to understand the input that they're making. Okay, so that's what the lab does, but what I want to talk to you today is about mobility. And so mobility is arguably the defining characteristic of our mobile devices. What makes them distinct from the kind of computers we're more familiar with in our offices is the fact that we can use them anywhere. But we don't actually just use them anywhere, we use them anytime. And so this image defines mobility concerns as I'm viewing them here. So it's not really that we can use our devices in any stable situation, it's that we use our devices in any situation we are in, including situations where we're occupied with other activities. So in this image here, we see a variety of people walking around a city, all engaged with their devices in a potentially hazardous environment. So here we have people walking across the street while they're browsing their social media. We have a driver on the social media in the car. And here we have clearly this issue of mobility, pressing people and restricting their cognitive abilities while they're out and about in a city. And so this notion of mobility is what I want to talk about today, and how this notion of mobility should impact the design of mobile and wearable systems. This shouldn't come as a major surprise, as it's been an established part of the public discourse for some time. If you look around Korea, you see this evidently. So this is a picture from downtown Seoul, which is warning pedestrians of the dangers, the hazards of using their mobile phones while they're walking. If you walk around Daejeon, you see that the pedestrian stop signs no longer have just a light in front of you. They also have illumination at your feet. And this is because the majority of people are busy on their smartphones, no longer looking up, they're looking down, and we need to signify this to those, the pedestrian crossing is available or not available to those people. So this notion of distracted walking has been kind of an aspect of mobility that is in the legislation. So this is what we do with our mobile devices, our phones, these current technologies. But how would these issues of mobility affect these wearable devices that I'm more interested in? So by wearable devices here, I'm talking about things like the Meta Quest 3, a recently released HMD, or Apple's upcoming Vision Pro. So this is a device we should see in the spring of 2024. So these devices not only provide a very rich visual scene to a user, they also provide a see-through scene. So they have cameras that capture the world outside, and they show that to a user. So you can walk around. You can wear this device when you are moving, walking, and living your life. So, if people are able to do this, just as they do now with their smartphone, what are the implications? How can we make input? How can we operate these devices in those mobility situations? So when we started working on this topic, this is one of the first questions we had. And so we actually tried to study this. How do people perform? How do they make input while walking in HMDs? So we did some initial work on this using a device called the Microsoft HoloLens 2. This again can project a scene in front of your eyes. But it has the additional property that has a see-through visor. It's like wearing a pair of sunglasses, so you can still see what you're doing. We looked at this problem of mobility on the Microsoft HoloLens 2 in terms of selection, so just choosing items. And in particular, the HoloLens 2 supports 3 mechanisms for choosing items. First, you can choose it with your hand. It's just like you would a mouse. You move your hand to point at an item in the distance. Second, you can orientate towards an item with your head. You can move your head to select an item. And third, you can look at an item with your gaze. So you can put your eyes on an item. Obviously, this is a combination of your head direction plus your eye direction. To try to understand how people select in this situation, we turn to standard methods in HCI. Particularly, we ask people to select a particular sequence of targets following an established method called Fitts law. Basically, we ask people to select targets in a circle that iterates. And this makes sure that we don't have any biases in the kind of selection people make. We also, because we're interested in how well they select, we chose a standard size for the targets, which is 3 degrees, which is kind of a chunky target you could view if you were viewing it on your computer. And we asked people to just stay on top of those targets for as long as they could. So we're just curious how well that selection process pans out. And then because we're interested in mobility, we asked people to do this while they're standing and also while they're walking. In particular, we asked them to walk a figure of 8 in a controlled setting around a classroom. So what were the results? Well, the results are pretty startling. So here we have a chart of the error rate, or the success rate, I should say. And so this is ranging from 0 at the bottom of the chart to 100% at the top of the chart. And then on the x-axis, we have the duration they were able to be successful. And this ranges from 100 milliseconds to 1 second. So in 100 milliseconds, you can't really do anything. But by the time you've selected something, being on top of something for a second, it's quite sustained, and it's certainly you have time to click it or otherwise select it. And so we see a huge break in performance. So along the top, the solid lines represent performance while standing. People are able to perform this, no matter what the modality of input, basically perfectly. But when people are walking, their performance drops precipitously. If we look at reasonable selection times of, say, 700, 800 milliseconds, success rates are below 10 to 20%. So in other words, people are unable to perform this task effectively. So this suggests that mobility, this mobile situation, will drastically reduce performance using these types of technology. You might ask, well, couldn't we just make the targets bigger? If people cannot select these targets, why wouldn't we just have bigger ones? And that's a good question. So here's the same plot, but instead of the accuracy, we look at the required size for targets to support an accurate selection. And again, we see that for a standing situation, we have a cluster of lines on the bottom, the solid lines. That suggests that people are really able to select more accurately than the manufacturer's recommendations with targets that are less than 2 degrees, less than 2/3 of the recommendation indeed. But when the targets when people are mobile, the required target sizes are between 2 and 3 times greater. And so in other words, we'd have to have extremely large targets that would start to occupy large amounts of the visual scene, obscuring the real world and also limiting the amount of content that could be presented. And so this suggests that this wouldn't really be a viable strategy, as people are maybe not going to be able to see enough content, and it's going to be quite frustrating. So this suggests that mobility is going to severely impact such devices. And this isn't a really simple task, just selecting a button, clicking a single item. What if we consider a more complicated task? So for example, what about typing? So typing is kind of a canonical task for mobile devices. It's one of the tasks that has fundamentally enabled the usefulness of these devices. Sending a message, entering some credentials, buying something, searching. All these types of activities are core to the smartphone experience. So typing is kind of a universal input activity on a smartphone. But so how does that And we've even, in fact, developed a particular modality for typing. This kind of a two-thumbed typing is very typical of the smartphone situation. So how does that contrast with typing on an HMD? This is a typical typing interface on an HMD. Somebody's wearing the device. There's a keyboard displayed virtually in front of them, and they hunt and peck for keys with either one or two fingers. So I would contrast these typing experiences. As for smartphones, I would say it's discrete, comfortable, and quick, by which I mean that it's something discrete, it's acceptable in public, something you can do wherever you are without feeling uncomfortable, without disrupting people. It's comfortable in that it doesn't cause you any physical discomfort, something you can do without feeling, for a sustained period, without feeling any exertion. And it's quick. People actually approach desktop typing speeds on their mobile phones, up to 38 words per minute. If we contrast this to HMD typing, I would say it's awkward, fatiguing, and slow. By awkward, I mean it's something you wouldn't do in public. It's disruptive. You have to make large motions that you may not be physically able to do, say on the subway. It may also be socially uncomfortable, maybe a motion that makes you embarrassed. So this is something you would not do. Those same motions are also fatiguing. They require you to raise your arms for sustained periods, which many people find tiring. And you have to do it for a sustained time because it's slow, between 6 to 10 words per minute. In other words, it's much, much slower, up to sort of 6 times slower than typing on your mobile phone. So current typing systems suggest for these devices suggest they're really not suitable for these mobile scenarios. So what we can do to improve that? Well, I'm going to show you several systems where we try to improve this situation. The first uses a dedicated hardware device. So here we see that device in action. So this device is composed of a set of fingernails mounted on top of cosmetic nails, just the kind of nails that you might buy in the store. And what we place on top of these is a set of touch sensors. And then we produce a keyboard composed of touches to those nails to enter text. A little bit more about what the hardware looks like. So you can see the nails in slightly more detail. There's a touch sensor on each nail. And actually, these are rich enough that we can sense a variety of different types of input from all the nails simultaneously. So we get quite rich data from these. In this particular text entry scenario, we're really only using single touches. We have a lot more. Okay, so if we've got a platform like this, how can we design a text entry system for these nails? How did we design this text entry system? Well, we considered various aspects, including comfort, because it turns out that for many people, touching their index and middle fingers is very easy. But as the touches move further and further towards their little finger, those actually touches become uncomfortable. So we need to take this into account in the design of our system. Otherwise, we'll have a system that fundamentally is not comfortable for people to operate. We also need to take account of speed and accuracy. So it turns out these types of touches can be made very rapidly and accurately. It's easy to touch the tips of your fingers in general. But we were concerned that while walking, actually that accuracy or speed may decrease. We conducted a study and found that it does not. Actually, there are no significant differences in this type of input between sitting and walking. This suggests this type of finger touch is really, really good for these mobility scenarios. And finally, as you have no doubt observed, the kind of input we're suggesting has only a limited number of inputs, many less than the number of keys there are in a typing system. So we need to try to figure out how to map multiple keys to each one of the available inputs in order to successfully support typing. So we basically need to look at co-occurrence of keys in words in order to create keyboards that can uniquely identify actually typed sequences of characters. So we use all of these as design concerns. Ultimately, we calculated data for each of these and optimized them using a genetic algorithm, and then selected a particular arrangement of keys that provided a meaningful, a reasonable mix of performances. This is a particular arrangement that we came up with. We generated 2 layouts. One involved a single touch to each finger, so there is 5 buttons, and another involved 2 touches, one to the tip and one to the side, which obviously had 10 buttons. We then contrasted these against standard QWERTY layouts of the same sort. And so the QWERTY layouts just map the QWERTY layout left to right onto the nails. We looked at how this performed, and actually it performs relatively well. So if we look at how fast people can enter text using our system, they can enter as up to 32 words per minute. So this is with our 5-key optimized layout. If we look how accurately, their error rates are incredibly low. They're able to perform this task really, really accurately. And finally, the comfort levels are very, very high. So particularly in our 5-key layouts, people found these are very, very comfortable to use. So what we can conclude is our optimized 5-key layouts were quick, accurate. Unfortunately, they were also ambiguous. Because we only have 5 keys, we actually have a low correct word prediction after people enter characters. It's easy for us to determine the wrong word from their sequence of entries. So any realistic system that uses this approach is going to require further development and word prediction. So this is our system for entering text using hardware. But obviously, beyond this limitation of word prediction, it also has a limitation, in fact, that users actually have to wear, maintain, keep charged a new device, a device such as their 5 fingernails. So can we do better? Is there some way that we can actually make the text entry task work in these HMDs that doesn't require somebody to wear such a device? Well, we moved on and tried to develop such a system. So here's a video of this system in action. So this uses a thumb typing system. So here we're inspired directly by the thumb typing that is very common on mobile phones. And the sensing here is of the fingers using only the sensors built into the HMD. So this is the standard tracking system is built into the HMD. Specifically here, what we're sensing is thumb taps to these buttons you can see in the main part of the screen, and index finger motions are signifying spaces and backspaces. So this is obviously broadly similar to our previous typing system, but has the advantage that it's no longer requiring a dedicated hardware platform. So what kind of design concerns went into developing such a system? Well, they're somewhat different than our previous system. So in this case, we have to be concerned with reachability. So in our nails, we looked at comfort to try to understand what fingers people can touch. But here we have a broader space of options. We need to understand where people can actually touch within this space above their hands. And so we consider a wide range of possible targets. And we observe that in the end, people tend to touch in this free scenario of touching any space above their palm. They tend to just make metacarpal joint rotations. So it's the first joint on the thumb. They tend to rotate only this, and they kind of use the thumb as a kind of hammer down. They don't tend to move left and right very much, and they don't tend to make other joint rotations. So this leaves us with quite a large range of selected targets. Unfortunately, most of them co-occlude. So they tend to be in a stack around this axis of rotation, and we cannot use them all. To deal with this occlusion issue, we fit a surface to these targets facing the thumb. So this surface is just a paraboloid that faces the thumb. And then we try to figure out how many targets we can actually realistically place on this, ultimately selecting 4 targets just at the quadrant centers of this paraboloid. With this system then, with a set of targets, you might wonder how it performs. Actually performs, in some sense, mixed. So we have very rapid performance, enough to support good typing, but very ambiguous. We had a very high error rate of up to 9%. So people tended to intersect the target they wanted and at least one adjacent target. To try to rectify this situation, we looked at various options. The first was we optimized the locations based on the set of actual movements people performed. This led to minor changes in location, but no real change in the performance. Ultimately, we observed that the intersections tended to be on the entry and exit of the thumb with the surface, rather than for the duration. So people generally touched the right item. Just when they were touching or removing their thumb, they tended to slide onto an adjacent item. So we focused on fixing this by looking at the full set of intersections between a paraboloid and the thumb in each touch, and using a deep learning classifier to try to identify the target from that full set of intersections. And this reduced errors by a factor of 4 to a level that's acceptable for typing. So for this, we then moved on to trying to define a keyboard layout for this system. Again, in this case, we focused on learnability. So here we're trying to support direct thumb typing. So we want to use something that's similar to QWERTY. So again, we considered many possible layouts, but only ones that were similar to QWERTY. So we tried to minimize the difference from QWERTY. In addition, we considered performance, again, as before, looking at the time and errors people make in their input. And finally, again, confusability. These are as before. This is our final layout that we achieved. Here, as I say, it resembles QWERTY, but then it's mapped onto this set of 8 keys. So in this system, we then finally evaluated it one more time, looking at novice and expert performance, and also looking at a difference between our typing system and a baseline, which is based on this kind of index finger hunt and peck. Here we observe that our system is very quick to pick up. It is equal to the baselines. People can type with our thumb system as easily as they can type with this more standard QWERTY implementation that you see in commercial products. In addition, our system showed very strong expert performance, so up to 27 words per minute, which is quite similar to what people can achieve with a smartphone. People can be really fast with our thumb typing. Further, it reduced exertion. So the fact that we have a hands-down thumb typing posture made people much less tired than with this hands-up posture that is the default. And finally, our system was also socially acceptable. People rated our system as suitable for use in most situations they would encounter day to day, very much as opposed to the system where their hands are up and they're typing in the air, which they rated as unsuitable. Okay, so that's what I wanted to conclude. That's what I wanted to say today. And so in conclusion, what I will try to summarize from what these projects illustrate is that current input techniques for smart glasses poorly support basic mobility scenarios, such as walking, or even just being out and about in the world. They're basically designed for these stable home settings, rather than settings that might encounter mobility. If we're going to design to mobility, we need to combine technical innovation with strong sensitivity to human factors. And by human factors, I mean we need to take account of issues such as comfort, familiarity, exertion, and social acceptability. If we don't, we will design systems and interaction techniques that are fundamentally not suitable for users, that they will not use. And so we need to look at the human factors of such technologies if we're going to make them successful. I want to acknowledge where most of this work was conducted, which was the Interactions Lab Design Department at the Ulsan National Institute of Science and Technology, and thank you for listening.